Can CHERI stop transient execution attacks? Hello, my name is Franz Fuchs, and this presentation is on to a transient execution attack mitigations on CHERI compartments. Transient execution attacks combine two mechanisms. First, there is directed speculative execution. That means that a processor is directed into executing a certain instruction sequence, and the second thing are side channels. Most often we use the cache timing side channel, but in theory we can use any side channel. On their own, these two are semi-powerful mechanisms, but when combined, they can become really powerful. And that's what I see in this example here. In the C code we see below, we have 3 lines. If index 0 is less than size, then we go into the if statement, access array 0 at index 0, and then use the value we get back to access array 1. The attack works as follows. The branch direction predictor behind the if statement is used to, or is trained such that it always predicts into the if statement. Therefore, an attacker can always provide an out-of-bounds value for index 0. Therefore, index 0 points to a secret. That secret is then index 1, and then we use that secret to access array 1. When we then look at the cache lines for array 1, where blue means that the cache lines are empty, we can see that we now have a cache line in, which we didn't have in before, and that is in direct correlation, excuse for the skewed, in direct correlation to the secret, and thus we have successfully encoded a secret in the cache. Transient execution attacks have become numerous. We now have Specter Meltdown and microarchitectural data sampling. They are widely applicable. They have been first demonstrated on x86 and ARCH64, and as we're going to be seeing later, they perfectly work on RISC-V as well. Unfortunately, they have become quite dangerous. Many of my collaborators have proved that they can potentially leak any microarchitectural state, and the speed is going up to multiple 100 kilobytes per second. There's multiple reasons for that and sources. We have branch direction prediction, indirect jump target prediction, return address, and so on and on and on. This list is far from exhaustive, and that's all microarchitectural state that can be used to leak secrets. So now we've seen the situation on commodity processors. How do secure systems, how do memory safety systems? So we looked at CHERI, which stands for Capability Hardware Enhanced RISC Instructions. The thing that CHERI does is that it brings in a capability. A capability is a pointer extended by metadata. The metadata is then mainly bounds information and permissions. What a CHERI capability then can do, it can not only describe memory, but also authorize access to it. On the right-hand side of the slide, you see a snippet of virtual memory, and within is a CHERI capability in the slightly bluish color. The pointer then allows access to everything within the lower and upper bound. This abstract CHERI ISA is then mapped as a security extension to any conventional ISA. Today we're obviously going to be talking about the CHERI RISC-V extensions. There are other ones, for example Morello, which is the ARCH64 extension for CHERI. Previous research showed that CHERI systems can be vulnerable to transient execution attacks. We reproduced the main 6 transient execution attacks, which are the 4 Specter attacks and the 2 Meltdown attacks that are most oftenly cited. All Specter attacks but Specter PHT have worked. Specter PHT is the one that is about branch direction prediction that can be mitigated with precise capability bounds. These results have been obtained on CHERI Tuber, which is a which is an out-of-order superscalar RISC-V softcore we are producing. So we believe that we can, with very careful design, build an out-of-order superscalar CHERI RISC-V core that can mitigate all of these attacks, but also remain performant. We had two main observations from that. The first one is that the microarchitectural design properties, rather than the CHERI ISA, determine whether a processor is vulnerable. That means our processor could have been vulnerable to all 6 attacks and still perfectly adhere to the CHERI ISA. And the second one is that transient execution attacks are not always harmful. They are harmful when they cross domain borders. And these domain borders might be within a protection unit, but the programmer has not yet found out that they're actually crossing a domain border. These two observations do not only hold for CHERI architectures, they hold generally for all architectures. So they are straight, perfectly mappable to RISC-V in itself. This brings us to a very, very bold statement. ISAs do not care about microarchitectures. When we look at RISC-V and the general design properties of actually all ISAs, we see that we have 2 things we are following. We are following generality, so it needs to suit all kinds of implementations, ranging from the microcontroller to the very sophisticated out-of-order implementation. What we dare do is that we avoid over-constraining at all costs. The second design point is the sequential programming model. ISAs always execute 1 instruction at a time. There's no parallelism, no out of order. And this is in strong contrast to what we are doing in today's very sophisticated microarchitectures. We execute multiple instructions at the same time and make extensive use of speculation in order to gain performance. So what we can clearly see is that a large gap has opened up between ISAs and sophisticated microarchitectures. And that then leads to insufficient ISA specifications. Speculative behavior in general remains unspecified. There are some bits in other architectures, for example, rudimentary barriers in x86. It has an LFANCE instruction, and that LFANCE allows not to execute speculatively beyond itself. We also can switch off some microarchitecture state if we want. Arch64 allows to switch off the memory disambiguator in its newest version. So now the question is, what is in RISC-V? Well, it is a big question mark. We have a microarchitectural side channel SIG. We are working, or some people are working on things, but in general, we have a big gap here. And that's what we call the microarchitectural specification vacuum. Architectures do not reason about speculative execution. And we really think that we should be reasoning about that. So we should do something what we call ISA level guarantees in order to have transient execution security. These guarantees can be used for two reasons. So we have, first of all, we need to test our microarchitectures against the ISA, and then these guarantees are the building blocks for software. With these building blocks, we can verify software against the ISA and can see whether an instruction sequence is vulnerable against transient execution attacks. So when we then look at how we design these guarantees, perfectly, we cannot prevent all speculative execution. That would be a trivial solution, but it would not be a good one because it would severely impact performance, and even the smallest microcontroller employs speculation these days. So the solution we are employing is to allow speculation within domains, but disallow speculation between domains. That brings us to the concept of architectural guarantees, which coexist then with domains. So architectural guarantees operate within a domain, and domains are protected against each other. In essence, what we are doing is we're performing compartmentalization in order to create these domains. The last question for this talk is then, how do we prevent transient execution attacks from crossing domains? In this scenario, we are having two compartments. We are having compartment A and compartment B. And compartment A wants to jump to compartment B. We are then employing CHERI compartmentalization. CHERI has something called sealed capabilities. It's a pretty simple concept. Sealed capabilities cannot be dereferenced, so they cannot be accessed. But what we can do in one atomic operation is to unseal this capability, so make it accessible, and then jump to it. So the sealed capability becomes a code capability, so the new program counter in the conventional world of compartment B. And that obviously brings us then in one atomic operation from one compartment to the other. The open research question remains is how can we enforce these compartments in speculation? The two main advantages with CHERI compartmentalization are that we have atomic domain transitions, meaning we have clean compartmentalization. Either we are in compartment A and remain there, or we are in compartment B. So we never leak any privileges between the two compartments. And the second big advantage is fine-grained decomposition. We can narrow down capabilities as much as we want. If we think back about compartment B could have been just a function of just a few bytes, and we can perfectly do that. So we can see that CHERI allows for secure compartmentalization mechanisms. In conclusion, we have seen that transient execution attacks are a threat to many systems. We also see that software cannot argue about transient execution security because it lacks the clear architectural guarantees. And that is what we are proposing. We want microarchitectures to uphold these guarantees. Finally, we see CHERI as the way forward. CHERI can enable us to do secure, fine-grained, and efficient compartmentalization. Thank you so very much. I have left a few minutes for questions, so please fire.
The compartmentalization that CHERI offers is like architectural, not micro-architectural, so it doesn't really solve the transient execution attacks, no?
Well, so what you get is when you have architectural compartmentalization, you solve the domain problem that you actually want to get privileges from one domain to the other one. While it helps in the first step, the next one is actually to enforce these guarantees, to make them clear, and then they're enforced microarchitecturally. So basically, once they are there, a processor does not adhere to the architecture anymore if it doesn't implement them.
Yeah, hi, great presentation. Just a very quick question. It seems like you're merging the microarchitectural model, the architectural model. And my question is basically that generally when we think about a microarchitecture, we design it such that it's very easy to program. So basically we have prediction because programmers repeat a lot of their code. We have caches because programs exhibit locality and temporality. And we have what most architectures have is a very strong memory model. So basically it's very easy to reason about multi-core systems. It seems that with your proposal, it seems that you expect the programmer to add special instructions within their program to guarantee isolation between different domains. And basically, my question is, given that you're merging both worlds, don't you think you're putting some strain in how a microarchitecture is designed? And second, do you actually expect programmers to make the right decisions when using these instructions in regards to performance?
Okay, I'll try to answer all of the sub-questions. You mentioned the right thing, memory models. Memory models is something where microarchitectural behavior is exposed in the architecture because it needs to be for portability. And that's the same reasoning that ISO-level guarantees for transient execution attacks follow. So we need to expose that, otherwise we have no guarantees from one implementation to the other one. There are no specific instructions because I follow the same, or we follow the same reasoning as you. We generally would not trust a programmer to insert them. What we can do is allow a compiler to reason about whether a certain instruction sequence is then secure. Do you have time for one more? Well then, thank you so very much.
Hello? Sorry, Nick. Actually.